All right, let's begin. First, I want to welcome everybody to today's webinar on CFD and its connection with cloud computing. My name is Michael Nee. I'm a product manager here over at Aerodynamic Solutions. Since I've been looking at the list of people coming in, I'm pretty certain that most of you are familiar with CFD, and that's probably not why you're attending. I assume that actually people are coming here because they are curious about cloud computing. And I think that the intention of today's webinar is really to give you an idea of what it is, its history, and how it's going to affect maybe your day-to-day lives as CFD engineers or aerospace engineers, and how it's going to affect you maybe in the future. Okay. So just I'm going to start with a little overview of what we're going to go through today. First, I'm going to talk about the history of the cloud. Then I'm going to talk about how CFD how CFD is a perfect application for cloud computing. We'll talk about the challenges of building a service for cloud computing infrastructure. We'll talk about our implementation of a service, Cloud Leo. I'll go through some case studies where I talk about turnaround time and costs, and then we'll finish up with some conclusions. Okay. Since everyone has varying ideas of what the cloud is, and I'm not certain what everyone's familiarity with it is, I'm going to start off with a very quick metaphor for how I see cloud computing. Okay, so what you see here is a little puddle on the street. This is ADS, and the little puddle represents the amount of computing infrastructure that we as a company can afford to budget every year. It's a very small amount. Okay, you may be a part of a larger organization, able with a very large IT budget and infrastructure budget, but you are like this lake. You're still bound by that budget. Okay, but with cloud computing, there is currently in development or is already developed what is equivalent to a sea of a compute infrastructure that is available to you at a price that is very much within reach. And that's kind of how I want to start off this entire presentation, give you an idea of where we're coming from and what we're going towards. Okay. So let's start with a little bit of history. I think, like most things on the internet, they really are started as they're really driven by the holidays, right? During this peak period, companies like Amazon, which procures so many items every holiday season, right? They have this huge uptick in traffic. And really, to ensure the security and uptime of their service, they have to build a lot of infrastructure to support this peak period. Okay, and that peak period is generally only a month long, right? So they build all this infrastructure, but to handle that one time of year. But really, for the rest of the year, it's completely unused, right? There's just not enough traffic to support it. And of course, the smart engineers at Amazon thought that this was inefficient, and really they wanted to develop an architecture that allowed them to sell this unused compute infrastructure, but sell it like a utility to many different customers, right? And so when they looked back at it and they tried to figure out, okay, how are we going to do this? That really required them doing two things, right? One is decoupling their software or their application from their hardware, okay? Second, and more importantly, is how do you expose this infrastructure to users with many different requirements, and then also have them want to pay for it, okay? So now I'm going to talk about where the word cloud came from and kind of how they did the first step. Now, Amazon was not, during the time that Amazon was doing this process of building what would be considered a cloud architecture. There were companies already existing that enabled the efficient use of internal clusters, okay, for various businesses, and they developed an architecture that allowed you to decouple the software from the physical hardware, okay, and they did this by creating what they call a virtual interface. They virtualize the physical boxes that you're on. And what that allowed them to do is it allowed them to put multiple operating systems that were virtually separated from each other. Okay, and it allowed them to communicate with the physical interfaces without interfering or interacting with each other. Okay, what this enabled was actually that now that they had these virtual interfaces, it allowed each of these operating systems, these customers, to be moved to different physical interfaces very quickly and very easily. Okay. Now it's this ability for one application to, rather than being stuck to one physical interface, it can now be virtually anywhere. It can be virtually on what is an amorphous cloud of hardware, right? And that's really kind of how the cloud came about, that cloud term. Okay. Um, let's pull it forward to today, and really cloud computing is not the buzzword it was maybe 10 years ago. It's supported by extremely large companies, and including OEMs, including Amazon, and this includes large companies like Microsoft, IBM, Google, Cisco, HP, and Salesforce. And what I think is really interesting is the whole cloud computing has really come full circle. And it's really this cloud computing infrastructure that is the enabling technology for the holiday peak shopping period today. So it's kind of come all full circle, and that's really what I found very interesting about the whole topic. Okay. So hopefully you have a little bit of idea of what the cloud is and what it can do for you. But now we're going to kind of tie the cloud into a CFD-based design system. Okay, so really, how does the cloud play an important role in today's design system? And really, when I talk about a design system, we're coupling things like methodology and software, but we have to also couple in the infrastructure. This design system, the goal of this design system really is design your product profitably and with confidence, right? And what the cloud addresses is the infrastructure part of this equation, right? And by infrastructure, I'm talking about things like not only the compute hardware, the physical servers, but the network infrastructure, the storage requirements, the power and the cooling and the maintenance, and the IT management. Okay. Additionally, the cloud addresses the upgrade cycle for these machines. Every few years, machines need to get refreshed with newer and newer computers, and these data centers, the cloud handles that for you. And what they were able to do is, rather than these being individual line items on a budget, they were able to combine this into one price that you pay every hour that you use one of their systems. Okay, so now the billing, the budgeting for the cloud use is much more simplified, okay, and much more efficient. And they can scale this because they're not just relying on one customer like we would be in a normal OEM. They're relying on multiple customers to make sure they have a lot of utilization on their machines, and that's where they make their money. Okay. I think now this is the thing that will really people here will understand quite a bit, and that is why CFD is a good candidate for cloud-based execution. I think we all know that CFD is very compute intensive. If you could run it on your local machine, why would you do that for these long-running jobs when they will basically shut down that one server? You won't be able to do very much. If you use a cloud-based a server, you can send it out to that server, still do your your Excel spreadsheets, your PowerPoint, your web surfing, or purchasing something on Amazon, right? You could do all of that while you wait for the computer, the computation to complete, right? And I think also what makes CFD a really good candidate for cloud-based execution is that really, we either have two situations as companies, right? Our budgets have limited the amount of installed infrastructure that we can have at our local facility, and this also limits what types of analysis we can do during one design cycle, right? So we are currently limited by our installed infrastructure. Second, if you really have enough money to build a cluster to do every single analysis that you want, you're really building to your peak usage. But if you build to the peak, it's typically something you might do once or twice during the design cycle, right? And just like Amazon, you have the problem where a lot of that infrastructure is unused. There's a lot of inefficiency. And I don't know about you guys, but for me, I hate inefficiency. And that's one of my driving goals when I build any product. Now I'm going to talk about some challenges. Whenever you build something to operate on this cloud infrastructure, there are a few things that you have to worry about. I think the first part of it is really understanding what the underlying architecture is and how it's going to compare against what you have locally. Okay. Second, we have to develop a secure architecture. Security these days, when we talk about the internet, anything connected to it is extremely important, right? So how do you develop that secure architecture? I think third, and as important, is the user interface, right? A lot of the people who are connecting to the cloud really don't have any sort of IT background. And so you don't want people to have to fight with trying to set up computers when that's not something they have any experience with. So you have to create a user interface that makes all of that disappear. Fourth, and I think this is as maybe more important than most things, is software licensing issues. Okay, and I'll go into that towards in the next few slides. So first thing is understanding what the cloud infrastructure is. And I'm going to focus specifically on Amazon Web Services cloud infrastructure. This is something that we have a lot of experience with. We've been working with them since about 2008. So I've worked with them quite closely. I don't want you to focus on this little eye chart down on the right. Really, I think what I want you to think about is, because Amazon Web Services, they have to build they have many different types of applications, many different types of users. It really requires them to offer a very wide range of servers of different performance levels and different price levels to service so many different and varying applications. Okay, just to kind of give you an idea of what you have to choose from, currently there are over 44 server types. You have to choose between 32-bit or 64-bit architectures. You can go up to 32 cores, up to 244 gigs of memory. You can do a normal compute or a GPU compute system. There are also 4 different network performance levels, and the range of price can be as little as 1 penny per hour to about $6.82 per hour. So there's a lot of options for you, right? And I think that the big question becomes, what is the best server for CFD, right? Amazon's not going to tell you, so we went through an exhaustive study to try and figure that out. Okay. Again, you can look at these, but I would say don't focus too much on the charts at this moment. I'm just going to give you an idea of what we observed when we did the analysis. I think when we were creating the cloud service, we wanted to do this pretty rigorously, and we had to do a validation study of various CPU performance and network performance of these various servers. So this study was commissioned really back in 2010. We worked with the United States Air Force to kind of get an idea how the cloud can be used for CFD execution. And during that commissioned test, what we did is we picked out of 44 types. We picked 3 types of servers, 3 general purpose servers of varying performance. We also picked 1 compute optimized server, which at the time was the most expensive server that they had. And we wanted to compare that against machines that were on our local cluster. Okay, here are the observations. Here are the takeaways from this analysis. All right. When we run 1 process per server, the general purpose instances or servers generally perform equally to that of the local cluster, meaning it is just dependent on the CPU core speed. Okay, so your turnaround time is based on the core speed. All right. But when we move to HPC type applications, such as those using MPI, large parallel processing, the performance of these general purpose servers really degrades significantly, more significantly than you would expect by having just a ton of computations going on. And what we discovered was that there was a large loss in terms of performance when doing parallel computation, as all the communication had to go through these virtualized network interfaces. The cost was so significant that it made HPC applications on those machines pretty much not usable, right? But during 2010, Amazon had already kind of envisioned that there would be a need for faster servers for scientific type applications, right? So they created these compute class servers. They call them compute cluster servers. And these are specifically set up for HPC. And the main difference is not the core speed or the number of CPUs. The main difference is the type of physical network interface that they have. And the network interface for those types of machines was very similar to that of what we have on our local cluster. Okay, when we brought those machines up and we ran our HPC simulations on them, we found that the performance was just as good as your local cluster, except now we had access to many, many, many more servers. So that was a pretty exciting time. I think at the end of it, our observation concluded that really these compute optimized servers are really suited for HPC simulations. And the cloud specifically is really suited towards either doing large, highly parallel simulations or many, many smaller simulations in parallel. Okay. Now I'm going to shift gears to the second challenge, which is developing a secure architecture. When we talk about security, we really have to build on top of other products. And I think at the base, it starts with the data center. When it comes to AWS, we're talking about various levels of compliance and certifications that their data center has received for securing various types of data. I don't know how many of you have ever purchased something from Amazon, but I know that they're doing millions and billions of dollars of transactions per day, holding on to securing credit card information. So that is what their bread and butter is, and it's securing that type of transaction. So I know security of the data center is extremely high. Okay, so that's at the Amazon level. For the cloud computing part of it, we have to talk about server security. Okay, so for every one of these cloud instances that you bring up, the servers themselves can be secured in multiple ways. One, they can be turned into virtual private clouds, okay, which would be essentially attached to your own network. Okay. Secondly, since the machines basically are attached to the internet, there is a firewall similar to what you have at your home, right? That is in front of every one of your machines that you bring up. Okay. And you can choose whether or not it has access to the internet or what types of communication can interact with each of your servers, right? So now that we know kind of how Amazon or the cloud is going to secure their machines, when we're developing an architecture, a secure service for this, we need some other related, we need something else. We need software related security. And what that involves is really we need to encrypt the transmissions to and from the cloud. We want to make sure that all the data that we send there does not permanently stay there. We don't want anyone else except ourselves to really own that data. We want to make sure that once the server is done with its job and deleted, everything related to you is gone. Okay. Second, lastly, we want to make sure that these servers that you bring up, the only people who can access it and look at the data that you're running on there are people within your organization, rather than people who are running the service for you. Okay. Next, I want to talk about building a user interface for our clouds. I think the goal of building a good user interface for this is to kind of first make sure that there's no IT know-how required. Okay, and we want to make sure that the user can't really differentiate between whether or not they're running on a local machine, their workstation, on some remote server that's part of their organization or on some cloud server that they've provisioned. Okay, but what is really needed is on the software side is a lot of back-end automation. Okay, to kind of remove all the IT know-how. We have to automatically set up and tear down cloud resources, set up those encrypted communication channels for you, compress the data to and from the servers so that we don't waste bandwidth, automate the upload and download of your simulation data, and then also have some kind of batching and queuing infrastructure so that you can efficiently use all that huge machine that you've just provisioned, right? Use it per hour. All right. Lastly, I'd like to talk about software licensing and start by saying really for everyone that the typical licensing structure of CFD software, right, is a blocker, right? I know many of you know this, but it's the fact that software is tied to a specific physical machine, that it's limited on the number of users, that you have some kind of limitation on the amount of parallelization that you can do, or some limit on the concurrent number of simulations that you do. And, really makes the current licensing structure not compatible with cloud infrastructure. And really what is needed is more flexibility, right? The cloud is really great when software is not attached to any machine, right? You pay only for the simulation hours that you use, similarly to the cloud, where you only pay for the CPU hours that you use, right? The cloud is only great if you can do, you have no limits on parallelization, or no limits on the amount of concurrent simulations you can run. So really, we have to build some kind of software licensing architecture that's going to fit well with the cloud. So I'm going to talk now about our service, which is Cloud Leo. What we did is we took our aerospace class CFD code Leo and we put it onto these cloud servers. And code Leo is this validated density-based solver that employs the cell vertex scheme. It's highly robust and highly accurate for turbomachinery problems. Okay, Cloud Leo is built for security. We looked at the architecture. We built all of the security that I suggested in the previous slides, where we encrypt transmissions. We make sure no data is permanent on the cloud. We delete the servers at the end, and we limit access to your machines to only people in your organization. So this service does not actually run any of the servers for you. Okay. Next, we built that intuitive user interface. We made sure that there's no IT support required for people who don't have the IT backgrounds. And lastly, we developed this pay-per-use software licensing model. Okay, and I'll go into that next. So what we created was this on-demand pricing. And like I said before, I think that the beauty of the cloud is that it allows for things like unlimited parallelization, unlimited concurrent simulations, unlimited users, and flexibility, a lot of flexibility. And we need a pricing model that is also as flexible. And so what we created was this metered pricing, which at the end of the day enables you to only be charged for simulations that you run. Okay, this on-demand pricing model not only monitors simulations that you run on the cloud, but it also can be transferred to simulations that are on your local computer. So no longer are you really thinking about two different pricing models. It's one pricing model for running both, right? Running locally and on the cloud. Okay. What we've done additionally is we've made the rates, the rate you are charged per hour, flexible depending on your usage level. You may not be someone who uses runs CFD that often, maybe once or twice per year for some design job. We call that the flex level. For people doing, for example, design cycles on a small centrifugal machine, 1 or 2 rows, we would move you to the everyday level. And then lastly, for people who are doing things like multi-stage axial compressors or axial turbines, we have a class called the industrial class, which is pretty much you're running almost full bore all the time. Okay. One thing I want to add here is that simulations under 2 minutes are free. Okay, and typically those are any cases that you configured incorrectly. So if you've done something wrong, you're not charged for an hour. I mean, nothing happens. Also, I think and more importantly, any 2D simulations that are run through the cloud typically take less than 2 minutes. So all of your design iterations on specific airfoil sections, that's all free. Okay. There's no limit on the number of concurrent simulations you run. There's no limit to the amount of parallelization that you have. And also, we enable it so that multiple contributors on a team can use these licenses. Okay. At the highest level, the rate per solver hour is 99 cents. Okay, and I know that doesn't mean anything yet, but we'll get into some case studies in a second that kind of show you what the price would be. All right. So the first case study that I want to show you is the generation of a compressor map, right? And I think for a lot of people that are viewing this webinar, they at least have some idea of what a compressor map is and how annoying it can be to run, right? Especially when you're limited by your resources, right? What we've done here is we've generated a compressor map for this NASA CC3 centrifugal compressor stage. It's both it has an impeller and a vane diffuser. Each of the red dots or red points here represents one case that was run, and each of the cases consisted of 635,000 elements. And we divided each of those restart files into 6 blocks and ran them for 8,000 iterations each. In total, to get this entire compressor map, it required 40 simulations and 240 cores. Right. If we wanted to do this on a local machine, it would take more than a week to get all the data. If we had access to the cores, if you had access to the cores, you would have to pay maybe $100,000 for the infrastructure required to do this simulation. But what I can do with the cloud is I can actually provision all these cores, 240 cores, execute all 40 simulations in parallel. Get the entire compressor map to be turned around in 2.5 hours. And the cost for all of those simulations is about $800 for both the compute and the solver time. And definitely this is dominated by the solver time, and definitely this is at the highest tier of usage. But at the end of the day, I think this gives you a good idea of what you can do when you have that power, and also how much it's going to cost you. And if you compare it to what you would pay for a normal machine, you can see that the economics now are really quite flipped, right? The next case study we have is for unstructured meshes or dense unstructured meshes. I think unstructured meshes are a great opportunity for CFD. I think everyone knows that generating meshes, structured meshes for very complex geometries is one of the biggest time sinks for an engineer in CFD, right? And unstructured has the possibility of opening up a lot of time and freeing up a lot of hands. But of course, unstructured meshes have their issues, right? For example, one is that generally you need more elements to get the same level of mesh density as a structured mesh. Okay. Second, a lot of solvers aren't very robust when it comes to mesh skewness. But however, Code Leo with its cell vertex scheme is actually extremely tolerant to highly skewed meshes. So very perfect for things like small tets, especially at, like, for example, the tongue of this volute where there are a lot of skewed meshes. Okay. So for this case, what we did is it's about 6 million elements. We partitioned it into 16 blocks and we ran it for 10,000 simulations, 10,000 iterations. I'm sorry. The turnaround time for this particular simulation was 5 hours, and the total cost was $90 for both compute and solver time. I think what's also interesting here is because unstructured is more easily parallelizable than a structured mesh. What this allows us to do is we can easily continue or increase the amount of partitioning that is done for this particular case, drive the turnaround time down, right, by adding more solvers. But at the same time, when we add those more solvers and drive down the turnaround time, our cost is still going to be about the same, right? So now we can say we have $90. I want to run this Vlut. How quickly can I get it done? I can apply as many of those solvers as I want. Now I can control the turnaround time that I'd like to have for my job. Okay. Okay. Here is a really interesting case study, and I think this is really where the cloud hits its stride, right? Because I think when we talk to a lot of turbo machinery companies, the one thing that they don't do often is large-scale unsteady simulations, things like full wheel analysis. And this is specifically because they don't want to buy the amount of computers that it's going to require to run these simulations. Secondly, the amount of the cost of the software to run these simulations is almost prohibitively too high. Okay, so the cloud really makes this accessible to really anyone, right? In this case, what we have is a 1.5 stage turbine. Okay, we simulated this as 1/5 of a full wheel, but you could easily do the full wheel if you needed to. We analyzed it for one full revolution, which was 10,500 time steps altogether with 20 inner iterations. In total, this simulation was about 200,000 iterations in total. The simulation also had a very high resolution, as each time step really represented only 1/2100th of a revolution. In total, this mesh was made up of 10.6 million elements, and we partitioned it into 160 blocks, executing on 160 cores. Right. The entire turnaround time for this simulation was 22 hours, and the cost was less than $2,000 for compute and solver usage. One thing I will add here is that because unsteady generally requires many more solvers than your typical steady simulation, the price for unsteady solvers is half that of what the steady solver license is. Okay, so we encourage you to use more unsteady licenses. But I think the advantage of the cloud really becomes evident, right? When you're talking about, again, the infrastructure you'd need and the software you would need to run this simulation, it would easily be over $100,000, right? But for $2,000, you're really talking about a drop in the bucket in terms of your IT budget just to get the simulation done. And by being able to do it, you can really apply a new level of accuracy that you can then pass on either to your designs or pass on to your customers and really differentiate yourself from perhaps your competitors, right? And really that's what we're all trying to do. We're trying to differentiate ourselves, right? Lastly, I'll talk about our company ADS. We're a small software and CFD consulting business. Okay, we focus on software, but we do CFD consulting from time to time. We use the cloud extensively. We validate all of our software on the cloud, okay, for regression testing. Second, for the consulting business, we use the cloud to execute large simulations that typically have only been limited to large OEMs to run. Okay, so we are able to provide a different level of accuracy when we talk to our clients, right? And I would really say that the Amazon Cloud resources is critical to our competitiveness. All right, so now I'm close to the end. I'm going to finish with some conclusions. I hope that everyone here today who's listening really can see that the cloud is really a very effective way to control your CFD-related hardware costs, okay, and maybe your software costs as well. For small companies, individual consultants, individual contributors, it really allows them to scale their CFD budget as demand builds rather than before it exists, okay. For medium and large companies, it really allows them to size their local infrastructure to whatever their typical usage is, and then use the cloud for a burst. And I think that it really opens up a lot of possibilities for everybody, right? It allows you to get greater insight, not previously accessible, because you're limited by IT, by your compute infrastructure. If you are not limited by that, then really it allows you to run additional simulations and improve confidence during your typical design cycle. So with that, I'm going to go back to that one metaphor at the beginning. Okay, this is ADS. We operate in a puddle of compute infrastructure. This is what our budget allows. If we were looking at the typical model of compute, right? Some people are much luckier and have a very large amount of IT budget that they can apply to what I would consider a lake of compute infrastructure. But there is this sea of compute that's being built, and it's not a fly-by-night type of application. We know that it's here to stay. It's changing the way the rest of these industries are being run, and there is a possibility that this will also change how we run CFD businesses in the future, right? It really allows companies like ADS to compete against the bigger fishes. Okay, and with that, I'd like to acknowledge that some of this analysis was supported by the U.S. Air Force Turbomachinery Group. And I will throw this last little tidbit out there. Anyone who is listening today who is interested in ADS software can get a free 60-day trial of the software. And with that, if you'd like it, just you can send an email to me at mlnee@adscfd.com. And with that, I will open it up for a few questions, if there are any. Sure. I have received a question from Barak Yanir. Can we describe other clouds? Yeah, I'll tell you the truth, Barak. I'm not particularly familiar with other clouds outside of Amazon. We haven't done extensive trials with them. Not saying that they are, not because we don't feel like they are not up to the par of Amazon. It's actually that other clouds may be just as usable as Amazon. So certainly our product can be moved to other clouds, but currently it is not. So I have a question from Guillermo. Uh, I can buy cores at a competitive price, but for times of emergency, your solution is ideal. Thank you, Guillermo. I mean, I think that's absolutely right. You can. There's always going to be a need to have your local clusters, right? Where I'm not saying that you use the cloud for all of your simulations, right? There will be times when those small simulations that you want to get done very quickly would be better suited for something that's local. But when you really are in times of emergency, or you want to do something that is outside of what your normal process is, you can really go and get that infrastructure very quickly. So another question regarding ITAR. Are there any issues with ITAR-related analyses performed using your cloud, using your software on the cloud? So that's a very good question, Jason. I think that ITAR restrictions are probably one of the biggest questions about using the cloud because of security. And though our software runs on any Amazon server. Not all of the servers are what they call ITAR compliant. Okay, so there are what they call government clouds that Amazon does run that is ITAR compliant, and you would be able to run it there. But in general, on general purpose servers, they don't guarantee that any of them are ITAR compliant. Okay, one more question is, can you talk about usage patterns? Do customers usually start with small scale simulations and build capability in the cloud over time? Or do they come to you to use the cloud for large jobs, which they can't do on their own? Is the cloud an emergency solution or a long-term capability building exercise for your customers? Thank you. That's a really great question. I think that in general, what we find, because we can operate both on the local machine and on the cloud, most people, when they're doing small simulations to kind of understand what their problem is, they will run that locally. Okay, so the small jobs are generally for their, the local machine. They want to fail, and they want to fail in their own little area. But once they're comfortable with how the software works, what the turnaround time is going to be, what the number of servers they're going to need, that is when they go to the cloud. And it's so, to answer your question, it's really, we find more people using it for large jobs. For example, they want to build a compressor map, um, which involves, at first you have to get the baseline simulation done. And when you do the baseline simulation, you run it locally because it's only one. But now when you want to run the compressor map, there's a whole lot of parallelism that can be taken advantage of. And so that's when they go to the cloud to go and generate all that data. I'll give you one example of a customer that we have who's running a multi-stage axial compressor on the cloud. And I think that's a really great case study. Generally multi-stage axial compressors are only limited to very large companies because we're talking about many, many rows and around 20 to 25 rows that have to be run all together, right? And generally, this for a small company, it would be something that they couldn't do, right? But with the cloud, they can get compressor speed lines very well within a reasonable amount of time compared to what they were used to. So I think that's where the bread and butter of the cloud is going to be. Okay, great. I think that's all the questions for today. And thank you for your time and spending about an hour with me. Again, if you have questions, just email me at mlnee@adscfd.com. And with that, I will close up shop. All right. Thank you, everybody.